get a practice on analyzing program constructs, consider the following program segment. The program segment consists of a for loop, a single for loop, followed by two nested for loops. Our first question, what is the input size? Remember that the input size is the problem size that influences the running time of the algorithm. And as you can see that the first for loop depends on a variable n, and if this n is increased, then the number of iterations also increased. And also if you look at the nested two loops, also they depend on the variable n. So the input size is basically the variable n. Our next question, how many comparisons are made at line 4? Specifically, the condition for the inner loop of the two nested loops. Let us find out how to find the answer for this question. The answer for the first question about the input size is n. So for part A, we have input size is n. All the formulas that we will write for time efficiencies will be expressed in terms of n. Our next question is the number of times the condition at line 4 is executed. And this condition is part of the inner loop. And as you remember, for any loop, the number of tests of the condition is equal to the number of iterations of the loop plus 1. So let us start writing the summation for this part. So here we say number of comparisons, Cn, is equal to summation of the inner loop, and the variable used for the inner loop is j. We can use the same variable for the summation, and we say j starts from 0 up to n minus 1 plus 1. In every iteration, we are making one comparison. So the answer for n minus 1 plus 1 is basically n. So this is equal to n. Now the inner loop is repeated by the number of times of the outer loop. So for every iteration of the outer loop, we are making the test of the condition this number of times. So therefore, we need to write the summation of the outer loop, and we will use the variable I. So I goes from 0 up to n minus 1, and this will be the answer for the number of comparisons made by the condition at line 4. Now we need to evaluate these two summations. So this is equal to summation. I goes from 0 up to n minus 1. And since we have a summation of 1, so the answer will be n minus 0 plus 1. So here we will have n minus 0 plus 1. And the answer for this one is in fact n plus 1. So this is equal to summation I goes from 0 up to n minus 1, n plus 1. Now since n plus 1 does not depend on I, so we can take it outside the summation and replaced by 1. And this will be equal to n plus 1. Summation that goes from 0 to n minus 1 will be n minus 1 minus 0 plus 1. And this is equal to n plus 1 multiplied by n. So this is equal to n squared plus n. And this belongs to big theta of n squared. Our last question is finding the efficiency of this algorithm using a quick analysis. Remember that for the quick analysis, we need to identify the basic operation of the program segment. Where to find the basic operation? You find it in a statement in the innermost loop. So this is the innermost loop, and this is the statement where we can look for the basic operation. This statement has an assignment operation, and it has two additions. And as you remember, that addition takes more execution cycles to execute than the assignment operation. So the basic operation is the addition at line 5. So here we write C, the basic operation is addition at line 5. So we can find the number of times these two additions are executed by using two summations. So here we say A of n, the number of times for the addition executed in the innermost loop, is equal to the outer loop summation, I goes from 0 up to n minus 1, multiplied by the inner loop summation, that j goes from 0 up to n minus 1, and in every iteration of the inner loop we have 2 additions, so the inner summation has 2. The evaluation for the summation is equal to summation I goes from 0 up to n minus 1, 2 multiplied by, now n minus 1 minus 0 plus 1, it will be equal to n. Now since 2n does not depend on I, so 2n can be taken outside the summation and replaced by 1. So this is equal to 2n multiplied by n minus 1 minus 0 plus 1, so it is equal to n. This is equal to 2n squared, which belongs to big theta of n squared. For the next example, consider the following program segment. This program segment is a dummy algorithm that has a single while loop with 2 statements as the body of the loop. The first part of the question is asking to determine the time efficiency of the algorithm by counting the number of iterations of the while loop. And in the second part, it is required to replace the statement at line 5 by the statement I takes the value of I plus 3 and then find the efficiency. Let us first solve the first part of the question, and then we will solve the second part after that. For counting the number of iterations of this loop, we need to identify its iterator. Basically, we are looking for a variable that is controlling the loop. This can be done by looking at the condition of the loop. Specifically, we look for a variable in this condition that is updated in every iteration. This variable is I because it is updated in every iteration. But this iterator is not simple because it is not updated by 1 in every iteration. However, its value is doubled in every iteration, so therefore it is not simple. Now by using this iterator, we can find the number of times the loop is repeated by listing all values of I received by the condition of the loop in every iteration. Then we build a summation from these values. Let me show you how. First, we will represent the number of times this loop is repeated by the formula Tn, which represents the time efficiency. This will be equal to summation, and now here we need to list all values of I received by the condition. The first value of I is 1. In the next iteration, it will be multiplied by 2, it will be equal to 2. This 2 multiplied by 2 will be equal to 2 to the power of 2. Again multiplied by 2, we will have 2 to the power of 3, and so on. All values of I are power of 2. And eventually, in the last iteration of the loop, its value becomes a number that is also a power of 2, and this number is represented by 2 to the power of k. Since we are counting how many times the loop is repeated, then we need to have 1 for the summation. So what does k represent in this summation and how it is related to the number of iterations of the loop? Remember that in the last iteration, the value of I is equal to 2 to the power of k. And at the end of this iteration, this value will be multiplied by 2 and becomes 2 to the power of k plus 1. The condition of the loop becomes false and the loop will stop. So k is the maximum power we will get for the value of I, and this happens in the last iteration of the loop. Let me explain to you by an example. Now suppose we have the value of n is equal to 17. Now let us list all values of I received by the condition. It is 1, 2, 4, 8, and 16. And all of these values are less than or equal to 17. Now when you go to the next iteration, which is in here, so when you multiply 16 by 2, you will get 32. and this 32 is not less than or equal to 17, the condition becomes false and the loop will stop. Now this is the last value obtained for the value of I, and it is represented by 2 raised to power 4. So what does 4 is related to number of iterations? This is for the first iteration, this is for the second iteration, third, fourth and fifth. So when n is equal to 17, this loop will go 5 times. So how it is related to the power? Notice that 1 is 2 to the power of 0, 2 is 2 to the power of 1, 4 is 2 to the power of 2, 8 is 2 to the power of 3, and finally 16 is 2 to the power of 4. Since this represents the first iteration, second iteration, third iterations, then we can find the number of iterations from the power of the values of I. So we can write the following inequality. We say that n is greater than or equal to 2 to the power of 4, and this is the last value we obtained for I in the last iteration. And once you increase the power 4 by 1, then we will get a value that is smaller than n. This will be 2 raised to power 5. Now this part of the inequality represents the test of the condition that is true in the last iteration. And this part of the inequality represents the condition when it becomes false after the last iteration. Therefore, n is bounded between two numbers, 2 to the power 4 and 2 to the power of 5. Now let us go back to our summation. Now this summation is not standard because the index is not increased by 1 and does not have a last value. But we can transform it into a standard summation, because in fact we need to count how many values of I do we have in this summation, and this can be found from the power k. So this is equal to summation. I will start from 0 because the first value of I is 2 to the power of 0, and the last value is k, and we have summation of 1. This is equal to k minus 0 plus 1. It will be equal to k plus 1. And we will label this formula by 1. But this is not the final answer, because the final answer should be expressed in terms of n, not in terms of k. We need to relate k to n, substitute into this formula to get the answer. First, we will assume that n is a power of 2. This assumption will simplify the calculations to get the answer. We will call this answer as the estimated answer. So let us start with this solution. So in the estimated answer, we will say assume n is a power of 2. Specifically, we will say let n is equal to the power of k. And from here, we need to solve for k. So take log 2 both sides. You will have log of 2n is equal to k. Now substitute for the value of k into this equation, and we will say that Tn is equal to k plus 1, and this is equal to log 2 of n plus 1. And this belongs to big theta of log of n in general. Now to get the exact answer, we will assume that n is any value, not necessarily a power of 2. This answer can be found by starting from the condition of the loop. So the loop condition is I less than or equal to n. So we will start from there. Remember that the last value of I in the last iteration is represented by 2 raised to power k. Substitute for the value of I. So here we will say 2 to the power of k less than or equal to n. And remember what happened when we increased the power of k in the last iteration. We had this inequality. So basically n is less than 2 to the power of k plus 1. This part for the condition if it is false, this part if the condition is true. Now take log of 2 in each part of this inequality. Take log 2. This will give us the following inequality. We will have k less than or equal to log 2 of n less than k plus 1. This inequality represents the floor of log 2 of n. Go back to the previous lesson, where this lesson is a quick review on the floor and ceiling functions and their formulas and properties. So here we say that log 2 of n is equal to k. Now substitute this value into formula 1. So we have t of n is equal to k plus 1. And this will be equal to floor of log 2 of n plus 1. And again, this belongs to big theta of general log of n. And notice that for the estimated and exact answers, we are getting the same efficiency, which is big theta of log of n. So what is the conclusion of this example? The conclusion is that if the iterator is multiplied by a constant, then the number of iterations is log of n, and the base of this log is the constant. So in this example, the iterator is multiplied by 2, so the answer is log 2 of base of 2. And if it is multiplied by 3, then the answer is log of n base 3, and so on. In the next part of the question, it is asking to update the iterator by adding a 3 instead of multiplying by 2. So this statement will be replaced by I is equal to I plus 3. Now how to find the number of iterations of this loop? We will follow the same steps as before. So to find out how many times this loop is iterated, then we need to list all values of I received by this condition in every iteration. So we write Tn is equal to summation. I will start from 1. As you can see, the first value is 1. And since we added 3 in every iteration, so the next value will be 4, next value will be 7, next value will be 10, and so on. So how to represent these numbers by a formula? As you can see that these numbers are multiple of 3, but we have a remainder. So either we can represent this formula by using 3k plus 1, or we can use 3k minus 2. So if the value of k, the initial value, is 0, we are getting 1. And if the initial value of k is equal to 1, 3 minus 2, also we get 1. So for this formula, the value of k will start from 0, 1, and so on. But for this expression, the value of k will start from 1, 2, and so on, until we reach the value of k in both cases. We will show you both answers. The first answer using this formula, the second answer using this formula. So let us start with the 3k plus 1. So here we have a 3k plus 1, and we need to find the number of iterations, so we have a summation of 1. Now we need to count how many values of I do we have in this summation. We will transform it into a standard summation by saying this is equal to summation. I is equal to, start from 0, it goes up to k, summation of 1, and this is equal to k plus 1, and this will be formula 1. Now for the estimated answer, we will assume that the value of n is equal to 3k plus 1. So here we will say assume n is equal to 3k plus 1, and here now solve for k. So n minus 1 is equal to 3k, and k will be equal to n minus 1 over 3. Substitute into formula 1. So Tn is equal to n minus 1 over 3 plus 1. And this will be equal to n minus 1 plus 3 over 3. And this will be equal to n plus 2 over 3, which belongs to big theta of n. Now to find the exact answer, then we need to start from the condition of the loop. So the loop condition is I less than or equal to n. Now replace the value of I by 3k plus 1. Then we have 3k plus 1 less than or equal to n, less than next value of k, which is k plus 1. It will be 3k plus 1 plus 1. Now we will subtract 1 from each part of this inequality. So subtract 1. We will get 3k less than or equal to n minus 1 less than 3k plus 1. Now divide by 3 each part of this inequality. We get k less than or equal to n minus 1 over 3 less than k plus 1. And then here we say that the floor of n minus 1 over 3 is equal to k. We can further simplify this equation by converting the floor into ceiling. There is a rule says that if we have a floor of n over m, this can be converted into ceiling. It will be equal to ceiling n plus 1 over m minus 1. So now for this equation, the floor will be converted into ceiling. So we will say ceiling n minus 1 plus 1 over 3 minus 1 is equal to k. And from here we have n over 3, the ceiling, is equal to k plus 1. And simply this is equal to formula 1. So we say that Tn as an exact answer is equal to k plus 1, and this is equal to the ceiling of n over 3. There is another way to find the answer without converting the floor into ceiling, and we will get this answer. How? Let me show you. In the beginning, what did we have? We have a 3k plus 1 less than or equal to n. Since the value of n is integer and 3k plus 1 is an integer, we can convert this inequality by rewriting it as a 3k less than n without the equality. This can be true if n is integer. If it is not integer, then you cannot do this. Let me give you an example. Suppose we have 5 plus 1 less than or equal to n. Basically, this is 6 less than or equal to n. Now, on the other hand, if you remove 1, then what you will get 5 less than n. But notice that these two inequalities will not be equal if n is not integer. If n is integer, is fine, because the next value of n that is greater than 5 will be 6, which is equal to 6. But what if we have 5.1? 5.1 is correct, but this is not correct because 5.1 is not greater than or equal to 6. So this step or this transformation, we do it if n is an integer and also 3k plus 1 is an integer. So let us do that on our equation. So from here we continue. What is the next value of k? It is k plus 1. We will say it is less than or equal to 3k plus 1. Because this part is for the condition when it is true and this part when it is false. Now we will continue from this inequality. So here we will divide each part of this inequality by 3, and we will get k less than n over 3 less than or equal to k plus 1. By looking at the definition of ceiling, because this is exactly the same as the definition for ceiling, we have the equality on the right hand side. But in the definition for ceiling, we need to rewrite it as m minus 1 less than n over 3 less than or equal to m. So we can find this answer by rewriting this inequality by saying that k is in fact k plus 1 minus 1 less than n over 3 less than or equal to k plus 1. So the value of m is basically k plus 1. So here we can conclude that ceiling of n over 3 is equal to k plus 1. And since Tn is equal to k plus 1, and this will be equal to ceiling of n over 3. So we are getting the same answer by relaxing the condition without going to conversion from floor to ceiling. Now let us consider the other formula. Now for the other formula, that if I is equal to 1, 4, 7, up to 3k minus 2. And here we will assume that k starts from 1 to up to k. So we will say that Tn is equal to summation that I 1, 4, 7 up to 3k minus 2 summation of 1, and this equal to summation I equal 1 up to k of 1, which is equal to k. So for the estimated answer, assume n is equal to 3k minus 2, and from here n plus 2 is equal to 3k, so k is equal to n plus 2 over 3. Substitute into this equation, we will say that Tn is equal to k, which is equal to n plus 2 over 3. This is equal to n over 3 plus 2 over 3, which belongs to big theta of n. Now for the exact answer, we will assume that n is any value. So the loop condition is I less than or equal to n. Now substitute the value of I by the equation. So we will have 3k minus 2 less than or equal to n. And this is less than 3, which is the next value of k is k plus 1 minus 2. Now add 2 in each part of this inequality. So we have a 3k less than or equal to n plus 2 less than 3k plus 1 without minus 2. Now divide by 3. We get k less than or equal to n plus 2 over 3 less than k plus 1. And here we have the floor of n plus 2 over 3 is equal to k. Now by converting the floor into ceiling using the transformation formula, we will say that floor of n plus 2 over 3 equal to k is equivalent to ceiling n plus 2 plus 1 over 3 minus 1 is equal to k. So we have ceiling n plus 3 over 3 is equal to k plus 1 by taking minus 1 to the other side. We do further simplification. Ceiling n over 3 plus 1 is equal to k plus 1. Since we are adding an integer inside the ceiling, we can take it outside. So this is equal n over 3 plus 1 is equal to k plus 1. Cancel 1 in both sides. Then what we will get is that the ceiling of n over 3 is equal to k. Now substitute into formula 1. So Tn is equal to ceiling of n over 3. Now we will find the same answer by relaxing the condition as we discussed before, without going through the converging from floor to ceiling. This can be done as follows. So we have the condition 3k minus 2 less than or equal to n, and this is equivalent to, because we are having integer n and k integer, 3k minus 3 less than n. So we subtracted 1 from this side and removing the equal sign from the inequality. So we will continue. We will say that 3k minus 3 less than n less than or equal the next value of k, which is k plus 1 minus 3. Take a 3 common, so k minus 1 less than n. And in here, in fact, what do we have? 3k plus a 3 minus a 3, so it will be equal to 3k. Now divide by 3 each part of this inequality. So we will get k minus 1 less than n over 3 less than or equal to k. And this is in fact the ceiling of n over 3 equal to k. Now substitute into the formula 1. So Tn is equal to k, which is equal to ceiling n over 3. In each case, this belongs to big theta of n. So what is the conclusion of this part of the question? The conclusion is that if the iterator is adding a constant in every iteration, then the number of iterations of the loop is equal to n over this constant. So in this example, the iterator is adding a 3 in every iteration. So the answer is n over 3. And if the iterator is adding 2 in every iteration, then the answer is n over 2. And if it is adding 5 in every iteration, the answer is n over 5, and so on. Before we end the lesson, we would like to have some examples on how to build a summation for a loop with certain iterator and condition, and what are the values of the index of this summation. In our first example, suppose we have the iterator I and it is initialized to 1. Let us assume it is simple, so it is updated by adding 1 in every iteration. So we write I takes the value of I plus 1 and assume that the condition for this loop is the square root of I less than or equal to n. So what will be the summation for this loop that represents the number of iterations? First, we will list all values of I that are updated in every iteration. So here we write I, the first value is 1 because it is initialized by 1. In the next iteration we add 1, it will be 2. We add 1, it will be 3. Let's assume up to k. Then the summation, we will use the variable I. And the first value of I is not simply equal to these values. Essentially, they are the values tested by the condition in every iteration according to the values of I. The first iteration, the value of I is 1. Basically, we are testing the square root of 1 against n. The next iteration, the value of I is 2. So the condition is testing the square root of 2. The next iteration, square root of 3. And in the last iteration, it is testing the condition for the square root of k. And this will be the summation of 1. This will be equal to summation I is equal to. Now, what is the first value of k in these numbers? The first value of k in these numbers is 1. The summation will start from 1 up to k of 1, and this is evaluated to k. Now, for the other example, suppose the iterator is initialized to 1. And if it is updated by multiplying by 3, so we have a 3i. And let us assume the condition we have is I cube less than or equal to n. So again, to find the summation, we will list all values of I that are updated in every iteration. So the first value of I is 1. The next iteration, we multiply it by 3. It will be 3. Next iteration multiplied by 3 will be 3 square. And the last value of I in the last iteration will be 3 raised to power k. So for the summation, what are the values we need to list for I in the summation? They are not these values. We have to look into the condition. The values that are tested against n are the cube of I. The first value of I is 1, so the first value of I in the summation will be 1 cube. Next value will be 3 cube. Next value will be 3 square cube, and so on. And the last value of I in this summation will be 3 raised to power k cube. This is equal to I is equal to. What is the first value of k? As you can see, the first value of k is 0. Why? Because 1 is equal to 3 raised to power 0. The first value of I is 0, and the last value is k of 1, and this is evaluated to k plus 1. Now for the next example. Suppose the iterator is initialized to n, and the iterator is updated by dividing I by 3. And let us assume the condition is log of I less than or equal to n. So what will be the summation for this loop? First, we will list the values of I that are updated in every iteration. The first value of I is equal to n. Divided by 3, we get n over 3. Divided by 3, we get n over 3 square. And in the last iteration, the last value of I will be equal to n over 3 raised to power k. So what will be the summation for this loop? We write summation I equal to, and we need to look at the condition for every value of I. The first value of I is n. The first value of I in the summation will be log of n. The next value of I will be log of n over 3. Next value will be log n over 3 square. The last value will be log of n over 3 raised to power k. And this will be the summation of 1. So this is equal to summation. The first value of I will be 0. Because the first value of I, we have n over 1. And this is equal to n over 3 raised to power 0. So the first value of k is equal to 0. It goes up to k of 1. And this is equal to k plus 1.